Hello and welcome to this appendix on the binary number system. All computer programmers need to understand binary numbers, and I'm going to simplify things a little bit to make that point. We have in front of us electronic machines. They're either plugged in or they're running on a battery, and the information inside them is stored. You can think of it as being stored as electricity. So we have either electricity is present or absent, 1 or 0. And this smallest piece of information is known as a bit. A bit of information can only have 1 or 0 in it. This is the only possible values. So you might recognize this symbol. It's a 1 and a 0 combined, and it's the on-off switch in some of your electronic machines. Well, one bit of information is not very interesting, of course, so if we start to put them together, ones and zeros, we have a collection of bits. If we put 8 of them together, we have something that's known as a byte. So we have a byte of information. It consists of 8 bits. I put a space there between the bits only so that it's easier for reading. This is typical. You'll see that large binary numbers have spaces every 4 bits for readability. Okay, what do these ones and zeros represent? And that's where the binary number system comes in. We have to find a way of representing values as a series of ones and zeros. So let's go back and start thinking about number systems in general. The number system that we're used to using, we've been using since preschool, is the decimal number system, or base 10, and the binary number system is base 2. In decimal we have 10 symbols, 0 through 9, to work with, and in binary we have only 2 symbols, 0 and 1. So as we put together decimal digits to make larger numbers, similarly we're going to put together binary bits to make larger numbers. Okay, here we are in a spreadsheet, and we're going to start this discussion of understanding binary numbers by first of all looking back at the decimal number system that we've been using since elementary school. And the decimal number system is base 10, and let's look at a decimal number 983 and remember what this means. So I'll start by breaking the number into its digits, or its component parts, and think about what each one means. Well, we know that 9 in the third place is 9 times 100, and this is 8 times 10, and this is 3 times 1 to make 983. When we say that this is base 10, that can be really thought about by saying, well, 9 is 10, 9 times 10 to the power of 2. 10 to the power of 2, 10 squared, is 100, and this is 8 times 10 to the power of 1, and this is 3 times 10 to the power of 0. Anything that's raised to the power of 0 is 1. So we have the ones place, the tens place, and the hundreds place, and of course this would keep going into the thousands place, the 10,000s place, and so on. So this is how I want us to start the discussion about the binary number system, by remembering what the places mean as base 10. So base means what is the base number with an exponent. 10 to the power of 2 means base 10 squared, and that's how we get the 100s place. So now let's start thinking about the binary number system. Okay, we're going to look at the binary number system now in the same way. So the binary number system is base 2, and we have only 2 symbols to work with, 1 and 0. So here's an example of a binary number, 1101. And what number would that represent, or what is that value? let's start taking it apart the same way we did with the decimal number, and we'll put the places here, 1, 1, 0, 1. Well, what does this 1 represent? In base 10, the 3 represented 3 times 1, or 3 times 10 to the power of 0. And we have something identical in the base 2 number system, except that the base is 2 instead of 10. So we have 1 times 2 to the power of 0. 2 to the power of 0 is 1. So this is the 1's place. So this 1 actually does represent 1 in the decimal number system as well. What does this 0 represent? It represents 0 times 2 to the power of 1. This 1 represents 1 times 2 to the power of 2. What's 2 to the power of 2? It's 4. And this 1 represents 1 times 2 to the power of 3. Okay. 2 to the power of 0 is 1. 2 to the power of 1 is 2. 2 to the power of 2 is 4. 2 to the power of 3 is 2 times 2 times 2, which is 8. And this goes on, but it turns out to be really very easy, because you can think of it as just write down 1 for the 1's place, and then we have the 2's place, the 4's place, and the 8's place. So instead of going up by powers of 10, as it did in the decimal number system, it's going to go up in powers of 2 in the binary number system. So let's go back to our number 1101. 1 times 2 to the power of 3 is 8. 1 times 4 is 4. 0 times 2 is 0. Anything times 0 is 0. And 1 times 1 is 1. So we have 1101 representing 8, 4, 0, and 1. And the sum of those is 13. So this binary number is the same value as the number 13 in base 10. Let's just review this briefly, because if you get this part, then the rest of it is kind of easy. The places in the decimal number system are the 1's place, the 10's place, the 100's place, and so on, and these are determined by powers of 10. The places in the binary number system are the 1's place, the 2's place, the 4's place, and so on, and these are determined by powers of 2. 2 to the power of 0, 2 to the power of 1, and so on. So the places in the binary system start by writing a 1 and then double it for each place moving towards the left. So here are some of the binary places: the 1's place, the 2's, the 4's, up until 128. There's a number of ways of trying to make you comfortable with working in the binary number system, but the way that I think it's a good place to start is to, the place that's a good way to start is to learn to count in binary. So we know how to count in decimal, and we'll start counting with 0. So what is 0 in binary? 0 is the same in all number systems. And then 1, and in binary it's also 1. In decimal, 2. We can't write a 2 here in binary because we only have the symbols 0 and 1 to work with. So go up here to your number system places and say, how would I write a 2? Well, 1 group of 2 and 0 groups of 1. So in binary we're going to write 2 as 1, 0 and throw that away. In decimal, 3, how would we write a 3 in binary? one group of 2 and one group of 1. In decimal, 4. How would we write 4 in binary? One group of 4, no 2's and no 1's. So now we have a 3-place number, 1, 0, 0. The number 5 in binary, are you getting the hang of this? A 4, no 2's, and a 1. So we have 1, 0, 1. Here's 6. A 4 and a 2, no 1's, 1, 1, 0. A 7. In binary, 4, 2, and a 1. Or 1, 1, 1. So counting in binary is an interesting place to start, getting comfortable with it. And you can keep going with this. It turns out to be not too difficult. You just can only put 1's and 0's in here to make the binary equivalent of a decimal number. Now, let's think about counting from 0 through 7. We have 3 bits representing all of the numbers 0 through 7, and that's not a coincidence. What is 2 to the power of 3? 2 times 2 times 2 is 8. We have 8 different numbers here, 0 through 7. Let's compare that to the decimal number system. Suppose we had 3 decimal places to work with. What is 10 to the power of 3? It's 1000. And we can represent the values in 3 places from 0 to 999. So 999 is the largest decimal value you can represent in 3 places, 3 decimal places. And in binary, 111 is the largest value you can represent in 3 binary places. 2 to the power of 3 is 8, and 10 to the power of 3 is 1000. So we might say that the largest value you can represent is 2 to the power of 3 minus 1. And the largest value we can represent in 3 decimal places is 10 to the power of 3 minus 1, or 1000 minus 1, which is 999. So we have 8 different values in the range 0 through 7, and 1000 different values in the range 0 through 999. Now let's think about why that's important. I wrote up here 8 binary places. So if I put a 1 in each of these places, what number would we have? 1111, 1111 in binary. And in decimal, how would we find out what value that is? It's the largest number we can represent in 8 bits, or 1 byte. Well, let's use that same idea. 2 to the power of 8 is how many different numbers we can represent, and I just happen to know that 2 to the power of 8 is 256. And if we think of it as what is the largest value we can represent there, 1111, 1111, 8 ones. I needed just a little more space there. That would be 2 to the power of 8 minus 1, which is, in decimal, 255. So now we have a way of saying what is the largest value we can represent in a certain number of bits. And this is the important one because bits come in bytes, 8 at a time, and you can represent the range of values 0 through 255 in one byte, and that's 256 different values. Okay, we're going to look at next some easy way to convert from binary to decimal, and you have to be able to do this by hand. So pencil and paper is a good idea. So converting small numbers from binary to decimal, we're not going to do millions, needs to be done on paper so that you are certain that you have an understanding of how this works. And then converting larger numbers from binary to decimal and from decimal to binary will be done with a calculator. And I'll show you a simple way of doing that on a calculator that I know you have. Okay, now we want to consider how we would convert a binary number to decimal. Suppose we had a 6-bit binary number, 110001, and we want to find out, well, what decimal value is that? First of all, let me point out that when we have binary numbers with more than 4 bits in them, we often will write a space every 4 bits. This doesn't change the number, the same way that we write commas in decimal numbers so that we can figure out what digits are in what place. So here's a binary number with 6 bits, and we need to know what is the decimal equivalent of that number. So let's take these bits and put them in their places. So going from right to left, we have a 1 in the 1's place, and we have a 0 in the 2's place, the 4's place, and the 8's place. We have a 1 in the 16's place and a 1 in the 32's place. So we now can see that this 1, the first one, represents one group of 32, and then we are just going to add these up. So that represents 16. We don't have to add up the zeros because they contribute nothing to the value, and we have 32 plus 16 plus 1. Let's see, what is that? A 9 there. So we have 49. This is the binary representation of the decimal number 49. So these are the same value, just different ways of writing them in the different number systems. Let's try another one. How about 111010, and I'll put the space in. Let's change it a little bit there. That makes it more interesting. And we're going to figure out what is the decimal equivalent of that number. First of all, before we start, do you think that this will be an even number or an odd number? The one that we just converted and found out that it was 49 is an odd number, and it ends in 1. Look at the value of the binary places. All of them are even except for the last one. When you add up even numbers, you get only even numbers. So if a binary number ends in 1, you can be sure that it's going to be an odd number when you convert it to decimal. So whatever decimal number this is, and I'm sure I don't know, it's going to be an even number because it's going to be the sum of even numbers. We have 7 bits here. Let's put them in their places where we have the value of the places written. So 0, 1, 0, 1, 1, 0, and 1. It's very easy to make a mistake doing this, so I'm going quite slow. 1, 0, 1, 1, 0, 1, 0. Let's add them up. 64, 16, 8, and 2, and those are going to add up to an even number. There's 10, 16, 20, 8 and 1 is 9. So we have 90. The decimal number 90 is 1011010 in binary. Well, some of you are asking right now, how do I know if I've mastered this? And you should be practicing this. We can just make up some binary numbers and see if you can come up with their decimal equivalent. And you can check your work on a calculator that's available to you as a Windows accessory. So if you look under Start, Programs, Accessories, you'll find a calculator as part of the Windows operating system. I keep mine on my taskbar. So here's the calculator that comes in Windows. Can I move it around a little bit so that you can see our conversions? The calculator has a View menu where you can change it between Standard and Scientific. So if you look at the scientific version of the calculator, you'll see that we have a decimal number system and a binary number system. If we click on binary, all of the digits are dimmed out except for 1 and 0, indicating that you cannot use any of the digits in binary except 1 and 0. So let's enter this number, 101 1010, and then if we convert that to decimal, we have the answer 90. So you can try some of these and verify that your answer is correct in the calculator that's provided to you under the accessories, and you can go back and forth between the decimal value and the binary value. I hope you'll have an appreciation looking at some of these binary numbers why we put the space every 4 bits, because writing down one of these binary numbers without making a mistake is really very difficult. Okay, what we're going to look at now is an easy way for you to convert from decimal numbers to binary numbers. So in this exercise we've gone from binary numbers to their decimal equivalent, and we're going to have to go backwards. If we have a decimal number, what is the binary number? Let's consider now how to go from decimal numbers to binary, and you can see that I've left the binary places up here. So we're going to work with numbers that are less than the largest number you can fit in 1 byte. Do you remember what that was? 255 is the largest number that would fit in a byte, and we're going to work on converting numbers that are less than that, and if we have to work with larger numbers, we'll do it just with a calculator. So let's start out with the decimal number 90, and I want to know what is the binary representation of that value. So we're going backwards from the last example. So let's look at the value of the places and say how many 128s are there in 90? Well, there aren't any. So you can put a 0 there if you want, but it's a leading 0, so it won't have any impact on the answer. Well, is there a 64 in 90? Yes, there is, so we'll put a 1 there. Now, if this 1 represents 64, we have these places left to represent whatever's left over after the 64 is taken out. So let's take out the 64, and I hope your arithmetic is better than mine. 10 minus 4 is 6, 8 minus 6 is 2, so we've got 26 left to be represented in these bits. Do we have any 32s in 26? No, so I'll put a 0 there. And then, do we have any 16s? Yes. So I'll put a 1 there, and we'll subtract out the 16, and we have now to represent the number 10 in these 4 bits. I'll take out 1 8, so if I subtract 8 there, I have 2 left. There are no 4s, 1 2, and no 1s. So the binary number that we have is 101. I'll put the space 1010. Okay, so now what we see is we have the same result as we had the last time, luckily, going from binary to decimal and from decimal to binary. Let's do another example. I'll throw all of this away. And let's take the number 213. Now, you might want to pause this and see if you can do it on paper without any help and without a calculator, and if you can, then you have mastered converting numbers from binary from decimal to binary. Okay, 213. Let's say, is there any 128s? Yes. Let's take out 128. This is the scary part for me because I haven't done arithmetic for a long time. Well, let's see. 128. Three minus 8, there must be a 5 there. 0 minus 2, there must be an 8 there. Go backwards and see if we got it right. 8 and 5 is 13. 8 and 2 and 1 is 11. Okay, so we've got 85 left to represent in these bits, sorry. Let's put a 1 there and take out the 64. 85 minus 64. A 1 there and a 2 there. So we've got 21 to represent here. There are no 32s. There is a 16. Let's subtract the 16. I did that again, didn't I? Subtract the 16, and we have now 5 left to represent here. No 8s, a 4 and a 1. So it starts to get easier towards the end. 1, 1, 0. 1 space 0, 1, 0, 1. Okay, so I'm claiming that that is the binary number, the binary representation of the decimal number 213, and we can always go to our calculator and check that, if I can get the calculator out of the way. So the decimal number 213, convert to binary 1101, 0101. So I encourage you to practice these on your own until you can convert numbers between decimal and binary in either direction with values up to 1 byte. If we had very, very large numbers, we would be doing them on a calculator. So let's just play with one. Suppose we have 1, 2, 3, 4, 5, 6. There's 123,456. What is that in binary? Well, there's a lot of 1s and 0s there. And you start to get a lot of places, a lot of binary places with relatively small decimal numbers. And that this is kind of an inhuman number for us to work with. I'm not even going to read this. This is a number that machines work with well and people don't work with well. So that kind of introduces the next segment. We're going to talk about hexadecimal numbers, the hexadecimal number system, which is base 16. Well, having done all of that, some of you are now asking, how do I know if I know what I'm supposed to know? I'm sure some of you were saying that. So here's an exercise for you. You can pause this recording and convert these numbers to binary, these decimal numbers to binary, and then there's 3 binary numbers that you can convert to decimal. If you can do these on paper and then check them on your calculator, if you can do these 6 conversions, then you can pretty safely assume that you've mastered this concept of converting between binary and decimal. Let's review the concepts from this appendix. We have the decimal number system that we've been using all of our lives, and this is base 10. And now we have the introduction of the binary number system, or base 2, and this is the number system that's used by computers to store information. We have a collection of 8 bits representing 1 byte, and this is for historical reasons. It was decided that the bits would come 8 at a time. If you need a value that can't fit in 1 byte or in 8 bits, then you use 2 bytes of information or 4 bytes of information, and so on. 1 byte can hold the values of 0 to 255, and we looked at why 255 is an important number in computing, and it's because all ones in a byte converts to the decimal value 255. I just mentioned that bytes are combined commonly to store larger values. If you need more than 255, then it won't fit in 1 byte. You're going to have to use 2 bytes or 4 bytes or 8 bytes or however many bytes you need to represent 1 value. And we've looked at converting from decimal to binary and binary to decimal, and I think it's pretty much required of all programmers that you understand this concept and be able to do this without a calculator for small numbers, and then for larger numbers, obviously this is something that the calculator is better suited for than pencil and paper. Thanks for watching this. I'll see you in the next appendix.